All right. So, as you've noticed, this did not go up over the weekend. I had recorded this in a couple other lectures and reviewing kind of the material that we want to cover for this class and what was actually built into the PowerPoints. I found that we were effectively getting into the weeds of information that is at a level I don't think is necessary for this here, for this class especially, as an intro to anatomy and physiology. So apologies for the delay on this. I am re-recording these. I am also modifying some of the slides, so I will upload this newer slide presentation. You will notice it is a good bit smaller than what it originally was. But this contains more of the pertinent information that I want you to actually know for the exams and quizzes. And moving forward, this is what we will be doing. I will be taking these very overcomplicated slide presentations and start breaking down the stuff that we don't really need in there, as well as in these videos really emphasizing what I want you to know. So with that, again, apologies that this is taking a little bit. This is a multiple attempt to get this recorded the way I want it so that it's not confusing for you guys and doesn't over inundate you with information you really don't need to be responsible for knowing at this juncture. So with that said, let's get into the chemistry of this. Now, by and large, when it comes to anatomy and physiology, the chemistry is not something I'm hyper fixating on. This isn't a chemistry course, and I don't need you guys to be able to really delve into the weeds of this. So our philosophy for this section is keep it simple, stupid, and do not delve into the weeds. I'm going to try and really emphasize things that I want you to know. So if it sounds condescending in any way, know that I'm not trying to do that. I'm just really trying to emphasize the stuff that I just want you to actually know. So with that, let's get started on this. So chemistry, yeah, it deals with the composition and characteristics of chemicals. That is, it is simply put, the most basic unit of chemistry is going to be the atom, right? So talking about the atom, how it functions, is going to be the real meat and potatoes of what I want you to know here. But additionally, chemistry plays a role in understanding the physiology and how these processes happen in the body. Things like food, liquids, medications, they're all composed of chemicals. Cells and their organelles are assembled with chemicals, yeah? So the chemistry is worth knowing. I'm just not too worried about you knowing all of the detail as it might be represented in a chemistry course. Okay. With these slides, what's highlighted is what's important. Matter. Everything that has weight or mass takes up space. It might be living, it might be non-living. That's matter. If it exists with physical properties in the world, it is matter. Yeah? All matter is composed of the elements. They are the elements that appear on the periodic table. Yeah? Elements are the smallest unit of matter with a specific chemical property. Elements, atoms, they're the same thing. Yeah? An individual atom is an element. An element is an atom. Now, you might have multiple atoms of the same element together, but an element is an atom. So living organisms require about 20 elements. Oxygen, carbon, hydrogen, nitrogen are the most abundant. I don't need you to know that hard fact, but know that living humans, oxygen, carbon, hydrogen, nitrogen, it's the most abundant thing, yeah? We are carbon-based life forms, hydrocarbon specifically, and we breathe oxygen, and nitrogen is in our atmosphere, so these are the most abundant elements. Again, elements are composed of atoms. But again, you can have multiple atoms of the same element, it's still the element, yeah? Atoms of different elements vary in size, weight, and interaction with other atoms, right? So different atom composition means it's a different element. Again, atoms, the smallest unit of an element. An element is an atom, and an atom is an element, right? Attractions between two or more atoms form bonds. And we'll talk about that more later. You don't need to necessarily know all of this in gross detail, like I mentioned before. What I do want you to be able to do here is just recognize these. Yeah, so these are the major elements of the body. Again, oxygen, carbon, hydrogen, nitrogen, that really is what composes us. Things like calcium, phosphorus, potassium, sulfur, chlorine, sodium, magnesium, that composes our muscles, our nerves, our bones, stuff like that. 99.9% of us is made up of these kind of things. You don't need to regurgitate them verbatim. Just kind of recognize them if I throw them out there in a list. They should be pretty recognizable, yeah? Compare this to a trace element. Now, a trace element is altogether less than 0.1% of our body. But as we talked in class last week, you would recognize these as like our supplements, yeah? Zinc, iron, manganese, iodine, fluorine, copper, cobalt, chromium. These are trace elements because we don't really need a lot of it in our body. Little goes a long way. They are trace amounts that we need. So again, you don't need to regurgitate. Just recognize that this list and that list look pretty different. This is our major elements of the body. These are our trace elements of the body. They make up less than 0.1%. An atom, the component parts, yeah? An atom is composed of a nucleus surrounded by electrons. The nucleus is composed of protons and neutrons. Okay, so the nucleus is your heart and soul of the atomic structure. Just like a cell, the nucleus holds all the DNA, right? In the atom, the nucleus holds the big stuff. It's the protons and the neutrons. So a proton is pro. It has a positive charge. It's about the same size as a neutron. A neutron, or neutral, is uncharged. It has a zero charge. Electrons, just know that they're negatively charged. They are so small. Again, if I am looking at myself as the size of a human compared to the size of an atom, that is similar in the difference of size between the size of an atom's nucleus and an electron. They are incomprehensibly small subatomic particles. An electrically neutral atom, that is to say, an atom that is not ionic, has an equal number of protons and electrons. Remember, when we're talking about ions, we're talking about the difference between protons and electrons. So if an atom gains an electron, that's an additional negative thing. It becomes a negatively charged ion. If an atom loses an electron, it becomes less negatively charged. And by comparison, we call that a positive ion. An ion forms when there's a difference between the protons and the electrons. That's what I want you to know. And to recognize if I gain electrons, I become negatively charged in my ion composition. And if I lose electrons, I become positively charged by comparison. When we talk about atomic mass and atomic number, again, just know the atomic number is the number of protons in an atom. Hydrogen has 1 proton in its nucleus. The atomic number of hydrogen is 1. The atomic mass, or the mass number, is the protons plus the neutrons. Remember, electrons are so incomprehensibly small in light that we treat them as if they, 1, barely exist, and 2, don't have a weight. So they don't affect the mass or the weight of an atom. Yeah? So again, if we're talking about the mass of an atom, it's the number of protons plus the number of neutrons. So if hydrogen has 1 proton and 1 neutron, its atomic number is 1, its atomic mass, or its mass number, is 2. Isotopes. Isotopes are the difference between the number of protons and the number of neutrons. Yeah? So all atoms that have the same atomic number, therefore the same number of protons, should have a similar number of neutrons, right? So all atoms of an element have the same atomic number because they share the same number of protons. Atoms with the same atomic number but a different mass, which must mean then a different number of neutrons, are called isotopes. So if we're talking about a difference between protons and electrons, we're talking about an ion. More electrons, negative ion. Fewer electrons, positive ion. The difference between the number of protons and the number of neutrons is an isotope. So carbon, for example, has 6 protons. If it has 6 neutrons, then it's a non-isotope. If it now has 7 neutrons, its atomic mass has changed from 12, representing 6 protons, 6 neutrons, to 13. It now becomes an isotope. It is different from the atom of carbon that has 6 protons, 6 neutrons. Same as if it had 8 neutrons, right? So the atoms of carbon that weigh 12, 13, and 14, as far as the atomic mass goes, the relationship between those atoms are that they are different isotopes. So if you have a sample of an atom, or a sample of an element, right? Like you have a big bunch of carbon. You likely have different isotopes in there because the different atoms in this collection of carbon elements probably have different atomic weights. So they vary a little bit in how many neutrons and protons they have between the atoms. And that basically means they have different mass numbers, so they're isotopes. Okay? So again, the difference between protons and neutrons create isotopes. Now, the addition of proton and neutron creates your atomic mass, right? So if carbon has 6 protons, 6 neutrons, its atomic number is 6 because it has 6 protons. Its atomic mass is 12 because there's 6 protons and 6 neutrons. But say I have a sample of carbon. So I have a lot of carbon atoms together, but they have different isotopes. So the atoms that have 6 protons, 6 neutrons are going to have an atomic mass of 12. Those with 6 protons, 7 neutrons are going to have an atomic mass of 13. And if I add in another neutron, an atomic mass of 14. The average between the different atomic masses is your atomic weight. Don't get in the weeds with this. Just understand, if I have a big chunk of carbon, right? That means I have millions and millions of atoms of carbon. The weight of that chunk of carbon is going to be representative of the average in all of the individual atomic masses of all of the atoms. So when you average the atomic mass together, that's the atomic weight of my sample. Okay? So again, an atom has a nucleus that is surrounded by electrons. The nucleus is composed of the positively charged proton, the no charge neutron, and the nucleus is surrounded by the negatively charged electrons, often referred to as an electron cloud. When there is a difference between proton and electron, so my atom gains more electrons in a reaction, it becomes a negatively charged ion. If it loses electrons in a reaction, it becomes a positively charged ion. We use the term ion because there's a difference between the number of protons and the number of electrons. The atomic number of that atom is just the number of protons. The atomic mass is the number of protons plus the number of neutrons. And when we change the atomic mass by changing the number of neutrons, but keeping the same element, keeping the same atomic number, therefore the same number of protons, we create isotopes. Isotopes individually have their own atomic masses. An isotope with 6 protons and 7 neutrons has a different atomic mass than an isotope with 6 protons and 8 neutrons. But when you average all of the atomic masses together in a big collection or sample of atoms or elements, we call that the atomic weight, because it's the average weight of the entire thing. Now, just understand, some isotopes are stable. Some isotopes are radioactive, which means they give off radiation in the form of atomic fragments. I don't need you to understand how radiation works. Just know that isotopes that give off radiation are radioactive. And if an isotope is radioactive, it therefore gives off radiation. So let's look at lithium. Lithium in this example has a nucleus composed of protons and neutrons. It has 3 positively charged protons, 4 neutral charged neutrons, and outside of the nucleus it has an electron cloud composed of 3 electrons. Now, we have an atomic number for lithium, and that's the number of protons it has. The atomic number for lithium is 3. It will always be 3, because if you change the number of protons, you change the atomic number. And if you change the number of protons, it's no longer lithium. Lithium's atomic number is 3. It has 3 protons always. Now, its neutrons are not always going to match. In this example, we have 4 neutrons. So we have an isotope of lithium in which we have 3 protons, 4 neutrons. When we look at the atomic mass of lithium, we add the protons and the neutrons. 3 plus 4, right, is 7. So the atomic mass of this lithium atom is 7. If we had another isotope of lithium where we had 5 neutrons, 5 plus 3, right, is now 8. So that would have an atomic mass of 8. If we took that sample together of a lithium isotope that had an atomic mass of 7 and a lithium isotope that had an atomic mass of 8, the atomic weight would be 7.5. Now, in this example, we have 3 protons and 3 electrons. So we have a neutrally charged lithium atom. If I add an electron to it and give it 4 electrons, we've added an electron. There is now more electrons than protons, and so we call this a lithium ion. That would be a negative lithium ion because there are more electrons, more negative than there are protons. If, however, we took this electron here and we got rid of it, there would only be 2 electrons. That would be less than the number of protons, so it's an ion. What's more? The number of protons. It's more positive now than negative, and so we have a positive lithium ion. When we talk about bonds, atoms form chemical bonds by attracting to each other. This happens by gaining electrons, losing electrons, or sharing electrons. And the type of bond that's formed will be told to us by whether or not we gained or lost an electron or are sharing them. Now, electrons exist in shells. When we draw them, it looks like this. This first ring here is our first electron shell. The second ring is the second electron shell. Atoms can have many shells, okay? So this lithium atom has 2 shells. The first shell, you just need to memorize this, has a maximum of 2 electrons. That is what makes the first shell happy. It wants 2 electrons. So before I can make a second shell for lithium, I first have to have 2 electrons. If lithium lost this electron out here, it would lose a shell. Okay, there would be no such thing as 1 electron on the inner shell, 1 electron on the outer shell. That doesn't exist. Before we can add a second shell, we have to fill the first one, which requires 2 electrons. Every shell after that holds a maximum of 8. Just know that. The first shell holds 2, everything after that holds 8. So, before we can add a third shell to lithium, we have to add 7 more electrons so that there are 8 electrons on the outside. That would be a very negative lithium ion. Then, if we added an 8th electron, that would make 9 electrons on the outside. Well, we can't have that because 8's our max. So we would create a third shell that had 1 electron. 2 on the first shell, 8 on the second, 1 on the third. That would be an even more negatively charged lithium ion. Atoms of elements that have their outermost shells filled are considered stable and therefore inactive, or what we call chemically inert. So this is not a stable atom of lithium. This is a reactive lithium atom because it has a second shell that doesn't have 8 electrons. It wants 8 electrons. Or it could give this electron away and then have a full first shell of electrons being happy at 2. If it had 7 more electrons, it would be stable. Or if it lost this electron and just had this 2 electron inner shell, it would also be stable. But because it doesn't have 8 electrons in its outer shell, or 2 electrons only having an inner shell, then it's not stable, and thus this is a reactive lithium atom. So let's take a look at these. Hydrogen has 1 electron, so it has 1 shell. Does that shell have 2 electrons? No, it does not. So is it stable? No, it's not. Because that shell wants to have 2 electrons. Now, hydrogen. Hydrogen has 1 proton, so its atomic number is 1. Hydrogen is unique. It does not have a neutron. Okay, so hydrogen's atomic mass is also 1. Fun fact, if you were to have a sample of hydrogen with millions and millions of hydrogen atoms, because all of them would have the same atomic mass of 1, it would also have the same atomic weight, 1. Looking at helium, 2 protons, 2 neutrons, 2 electrons. Is it an ion? No. The number of electrons is equal to the number of protons. So it doesn't have a charge. It has 1 shell. Now, that first shell has only 2 electrons, but that's okay because the first shell only wants 2 electrons. So is it stable? Yeah, it's stable because it only has 2 electrons, but it only has 1 shell. And that first shell wants 2 electrons, so this is stable. Yeah? Could it react? Sure. We can turn it into an ion and it will become reactive. But currently, it is unreactive or chemically inert. Now, 2 protons, 2 neutrons, 2 plus 2 is 4, so the atomic mass is 4. The atomic number is 2 because it's the number of protons. Okay? If I add an electron to helium, because the first shell is already filled of its 2 electrons, we would add a 3rd shell. Okay? Now it would be chemically reactive because it doesn't have 8 in the outer shell or just an inner shell of 2. It would also have more electrons if I added a 3rd electron, so it would be a negatively charged helium ion. If I removed one of the electrons, it would be a positively charged helium ion. Now, if I added another neutron, that would be an isotope with an atomic mass of 5. Now, if I had 2 isotopes, one that was an atomic mass of 4 and one that was an atomic mass of 5, again, the atomic weight is now 4.5. I'm not going to really ask you to ever calculate atomic weight. That's just kind of a dumb exercise in math. But just know that the atomic weight is the average of all of the atomic masses, depending on how many atoms there are. Okay. Let's look at lithium. We just did this example. Yeah, 3 protons, 4 neutrons. Is it an isotope? It sure is. It's an isotope with an atomic mass of 7. Now, lithium is reactive because it has an outer shell that does not have 8 electrons. It has 1 electron in its outermost shell. It could become an ion by losing an electron, become a positive lithium ion. That would actually make it somewhat stable. It would stabilize it because now it has 1 shell with 2 electrons and that's all it wants. Or we could add 7 electrons, make it a really negative lithium ion that is also stable because now the outside has 8 electrons, okay? Bonding. Let's talk about the multiple forms of bonding. I'm going to be real specific about what I want you to know. When we talk about ionic bonding, these are atoms with incomplete outer shells. So they're reactive. Lithium is incomplete. Hydrogen is incomplete. However, in order to form a stable outer shell of 2 electrons, when we talk about ionic bonding, 2 or 8 electrons, sorry, depending on which shell we're in, We are talking about bonding that exists exclusively between ions, right? So when atoms gain or lose an electron, they become an ion. Whether they gain or lose the electron will tell us whether or not it's a positively or negatively charged ions. Things with opposite charges form ionic bonds, okay? Let's wait for our example. So if I have a positive ion and a negative ion, right? They're going to have a relationship with each other because they're opposite charges, they're going to attract. Now, they don't form molecules, so they don't actually form new molecules. Rather, they align themselves next to each other because of their attraction, and we call that a crystal array. Okay? So, for example, if we have a sodium atom, an atom, right? And it contains one electron in the outer shell. That shell wants to have 8 electrons, right? So it has an inner shell with 2 electrons. Let's look at the example. Okay, sodium has an inner shell of 2 electrons. Now, in this example, sodium actually has a second shell fully filled, 8 electrons, but it has a third shell, right? A third shell with 1 electron. So 11 electrons, okay, and 11 protons. This is a neutral atom of sodium, okay? And we can do the exercise down here. What's its atomic number? 11. Why? Because 11 protons. What's its atomic weight? Okay, or atomic mass is the proper term. It's 23, okay? 11 plus 12 is 23. Now there's 11 protons, 11 electrons. It's not an ion, okay? It's also not an isotope because it doesn't have a difference between number of protons and neutrons. But let's look at sodium chloride. That is a common salt. It's table salt, basically. Well, iodine chloride, right? Sodium iodide, sorry, is table salt. But this is a salt. So we have chlorine. Let's ignore the rest of the chart for a second. We have chlorine. 17 protons, 17 electrons. This is a neutral atom of chlorine. But when we break it down, look at this. Its outer shell has 1, 2, 3, 4, 5, 6, 7 electrons. It's missing an electron to become stable. Well, sodium over here just so happens to have 1 electron in its outer shell. Now, does it make more sense for sodium to try and steal 7 electrons from chlorine? Or does it make more sense to, hey, give up this 1 electron and then drop down to only 2 shells where there's 8 electrons? The chemical answer is these 7 electrons have way more power to rip this 1 electron off than this 1 electron has to rip these 7 electrons off. So what happens is when these 2 atoms get close together, chlorine is going to rip an electron off of sodium. It's going to gain an electron. Now it's super stable, okay? But it's now an ion. It's attracted negatively. When we have that sodium ion losing an electron, it becomes positively charged. It's stable, right? But it's positively charged. Negative and positive are attracted to each other, so they form a crystal lattice. Notice in the chemical compound sodium chloride, these do not bond together physically by sharing electrons. Rather, they bond together through electronegativity. Electromagnetism, negative and positive. So they hover next to each other in a crystal-like array that we call sodium chloride. That is an ionic bond. What do I want you to really know about ionic bonds? It is a reaction between 2 ions that form crystal arrays. That's it. That's what I want you to know. When you have 2 ions of opposite attraction, they form an ionic bond, sometimes referred to as an electrovalent bond. Why? Because the last shell of an atom is called the valence shell. So the valence wants to be satisfied. So we lose an electron here. So electrovalent. Ionic bonding occurs between two ions that are opposite charges, okay? And what I want you to know is we don't call these molecules, we call them crystal arrays. It's just the special orientation that they form when the negative and the positive line up next to each other. It's like batteries, okay? Covalent bonding. So, what's electrovalent bonding? Electrovalent is when we change the electricity or the electron and we make an ion. So we have two ions next to each other, holding each other close together through attraction of negative and positive charge being opposite. Ionic bonding. Covalent means we share in those valent electrons. So I'm not ripping an electron from one guy and giving it to the other and creating ions. Rather, these two non-ionic atoms get close enough together where their electrons are shared between them. They co-share their electrons, covalent, okay? Now, this is where we get the traditional bond drawings that we'll see in a second. So if I have two atoms and they each share with each other one electron, let's look at hydrogen again. Look at hydrogen. Hydrogen has one electron. If two hydrogens are next to each other, they're not going to rip electrons off each other. Rather, they're going to work together and they're going to say, hey, I'll share my electron with you if you share yours. Together now, we share two. And our valence shells are happy because they have two electrons. Because they each share only one electron, we call it a single covalent bond. Now, we can share two electrons apiece, which we call a double covalent bond. We can also share 3 electrons apiece. We call that a triple covalent bond. We can't share 4, okay? It just doesn't exist. Now understand, when we say a single bond, we mean 2 electrons, 1 from each. When we say a double bond, that's 2 from each, so there's 4 electrons composed in that bond. And the same goes for triple, it's actually 6 electrons. So hey, look at hydrogen. Hydrogen is not going to rip electrons off each other. Rather, their nuclei are going to float close by to each other, and these electrons are going to be shared between them. Now, in this drawing, we show an overlapping of the shells, but remember, electrons are really a cloud. So what we really have are these 2 nuclei composed of the hydrogen single protons, and then these 2 electrons hover around the whole thing together. There's 2 of them around everywhere at once, and that is what we call a covalent bond. Now, it gets a little tricky with covalent because there's 2 special types of covalent bond, polar and nonpolar. I do not need you to know how to calculate whether or not a bond that forms covalently is polar or nonpolar. All I care that you know is that a polar covalent bond is going to share electrons unequally. Remember, the electron cloud is constantly moving. These electrons are just flying around the nuclei very quickly. In this example, they share it equally. So together, these electrons travel around each other very equally. They don't spend more time around this nucleus and then come over here for a little bit and come back. They fly around the nuclei equally. That is a non-polar covalent bond, which I think we're not talking about until later. That was my fault, sorry. So polar covalent bond is a molecule in which the electrons are shared unequally. So they reside closer to one atom than the other more often, okay? These molecules create an unequal charge distribution. So think of them similar to ions. They have a more positive side, because that's where the electrons spend less time, and they have a more negative side because that's where the electrons spend more time, okay? I want to use an example. So here is water, right? 2 hydrogen, 1 oxygen. Now, oxygen is very powerful in its attraction to its electrons. It doesn't like to share. It will share because oxygen and hydrogen in these examples are not ions. They are forming a covalent bond. Oxygen, and you don't need to memorize this, I just am telling you, oxygen has 6 electrons in its outermost shell. So it needs 2 electrons to become stable. Hydrogen has 1 electron in its outer shell, so it needs 1 electron to become stable. So it's going to create a single covalent bond with oxygen here and a single covalent bond with oxygen here. When that happens, because oxygen is greedy with the electrons fly all across the water molecule, but they spend more time over here. And then they cycle over here real quick, and then they spend more time over here. Because of the concentration of electrons over here, the oxygen side of water is going to be slightly negative. Because the electrons spend less time around hydrogen, the hydrogen side of water is going to be slightly positive. It's not an ion. It's not truly negative. It's not truly positive because they are sharing the electrons. So it is a covalent bond, but it's a non-polar covalent bond. Again, I don't need you to be able to tell me based on a molecule if it's going to be polar or non-polar. Yeah, I'm sorry, I misspoke. It's going to be a polar covalent. Sorry, that is my mistake. Polar covalent bond because there is a pole. The negative side is slightly more negative. The positive sides are slightly more positive because the electrons share unevenly. That creates polar charges. There is a slightly negative side, slightly positive side. It is a polar covalent bond. Versus hydrogen, that they're the same atoms, so they're going to share evenly. Neither of these nuclei are more attractive of their electrons, so they share evenly. That is a non-polar covalent bond. There is no slightly negative, slightly positive side to this molecule. These two atoms interact, they form a molecule, those electrons fly around symmetrically, so therefore there's no pole. There's no slightly negative, there's no slightly positive. We call that a non-polar covalent bond. So, when I talk about a covalent bond, my question might be, what kind of bond forms between two atoms that when they make a molecule equally share their electrons? Well, I already said they make a molecule. So it can't be ionic bonding because ionic bonding does not make a molecule. It makes a crystal array. So already I'm telling you it's a covalent bond. Now, if I say they share their electrons equally and they do not create poles, that must be a non-polar covalent bond. So if I say, what kind of bond is formed by two atoms that share electrons equally, that makes it a non-polar covalent bond. If I say, what kind of bond is formed by two atoms that share electrons unequally, creating a slightly negative and slightly positive side, well, that is a polar covalent bond. And that is how I might ask the question. I could also just say, what kind of bond is formed by sharing electrons? A covalent bond. What kind of bond is formed by creating ions? An ionic bond. Yeah? Now, there's a special mention here, a hydrogen bond. A hydrogen bond is kind of the leftover garbage, yeah? A hydrogen bond is a really weak bond that exists simply between hydrogen and something else. So, looking back at water, okay? We have water made up of two hydrogens and an oxygen. Oxygen is greedy with its electrons. It won't rip the electrons off of the hydrogen, right? So it won't create ions. They'll covalently bond. It'll share one electron with this hydrogen who will share back, creating a single covalent bond. And then it will share one electron with this hydrogen over here who will also share an electron, creating a single covalent bond. This will be a water molecule. And because oxygen is greedy with how often it pulls the electrons to its side, it is a polar covalent bond because it creates a slightly negative oxygen side and a slightly positive hydrogen side. Now, the slightly negative oxygen side and the slightly positive hydrogen side will be attracted to each other, and that will hold the different molecules of water together in a big tub of water. That attraction between the slightly negative oxygen side and the slightly positive hydrogen side is your hydrogen bond. Again, it's not a true attraction that's strong because these aren't ions. It's not a negative and a positively charged ion. It's a slightly negative side of a covalent polar bond, bonded molecule, slightly attracted to the slightly positive side of this polar covalent molecule. Yeah? So it's not a strong bond at all, but it exists in a lot of chemical structures. So when I ask about hydrogen bonds, my question might be, what kind of bond is formed between two polar covalent molecules that forms between the positively charged hydrogen and the negatively charged end of another polar covalent molecule? Something like that is the hydrogen bond, yeah? The hydrogen bond, what is, another way I might ask it is, what kind of bond is formed between hydrogen and something else in a polar covalent molecule? Yeah, it's something along those lines. If I ask anything like that, your answer is hydrogen bond. As soon as I mention hydrogen, you should already be thinking hydrogen bond, especially if I say weak. Yeah? So the three bonds, ionic. If I have two ions, one negative, one positive, they bond to each other ionically, okay? They create a crystal array. So if I have sodium and chloride, chloride rips an electron off of sodium, creates two ions. Those ions are attracted to each other. They do not form a molecule, but they do form a crystal array. Covalent bonds, they share electrons equally. How many they share is how many bonds they're forming. If two atoms are sharing one electron apiece, it's a single bond made up of two electrons. If it's two electrons apiece, it is a double bond totaling in 4 shared electrons. And if they share 3 electrons, it's a triple bond totaling 6 total electrons. In a covalent bond, if they share electrons equally, it is non-polar. If they share it unequally, it is polar. When they share it unequally, understand that means one side of the molecule is slightly negative, the other is slightly positive. If they are weakly attracted to each other via the hydrogen side, it is a hydrogen bond. That's what I want you to know. Now, molecule and compound. A molecule is formed when 2 or more atoms create a bond, okay? Specifically a covalent or a hydrogen bond, okay? If an atom of the same element bonds together, it forms a molecule. So if oxygen bonds with oxygen, right, it's going to have 6 electrons in its outer shell. So it needs 2 from each other. So it's going to share 2 electrons apiece, which means the total number of electrons shared is 4. That means they're going to double bond together. Now, because they're the same atom, they're not going to have the ability to create a polar bond between each other because they're equally as strong. So it's going to be a nonpolar covalent bond. Because it's the same element, we just call it a molecule. Yeah? If the compound that we're looking at is a molecule with different elements in it, we call it a compound. Again, so if I have O2, it's 2 oxygen. That's the same element. It's just a molecule. If I have water, well, now we have a molecule still because it's different atoms bonded together, but we have hydrogen and oxygen. Well, those are different things. So we call it a compound molecule, okay? So if 2 atoms of hydrogen form a non-polar covalent bond, we call it a molecule. If 2 atoms of hydrogen and 1 atom of oxygen form a polar covalent bond together, it's still a water molecule, but because there's 2 types of elements in it, we call it a compound molecule. Okay? So since it contains the different atoms, it's simply compound. If it's the same stuff, it's a molecule. If it's different stuff, it's compound. Still a molecule, it's just a compound molecule. So again, on the left, we have 3 molecules. We have 2 polar covalent single bonded oxygens. Yeah. If we have, we also have a oxygen molecule, right? We have a polar covalent. We're not sharing 2 electrons, we're sharing 4. So double bonded oxygen molecule. We have 2 hydrogen molecules. We have 1 oxygen molecule. Together, these will now interact in such a way that they will form 2 non-polar water molecules. These molecules of water are compound molecules. Okay, and notice when it's oxygen and oxygen, because they need to share more to get to 8, it's a double bond. But because we have 2 hydrogens here, now oxygen just needs to share 1 here and 1 here. It's 2 single bonds. Molecular formula. A molecular formula is just how we write it such that we identify the atoms that are present in a molecule. So in a molecular formula, I'm describing what atoms are present. So let's look at water. H2O, the molecular formula is H2O. The molecular formula tells me how many types and number of atoms there are. In water, I have 2 hydrogens, 1 oxygen. If I look at glucose, C6H12O6, I have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Okay? That is the molecular formula. It tells us the number and type of atoms involved. Okay? Now, you'll notice nothing about a molecular formula tells you what kind of bonds are going on. It never does. So it's not going to factor into the kind of bonds unless you're just memorizing it. Now, a structural formula is a little bit different. A structural formula does tell us how these things are bonded together. So each atom forms a specific number of covalent bonds, and based on the number of electrons that it shares in its outermost shell will tell us a bit about its structural formula. So hydrogen atoms form a single bond together because they each have 1 electron, so they share 1 together, 2 in total. That's a single bond. Oxygen atoms form double bonds because they have 6 electrons, so they need 2 from each other. That means a total of 4 are being shared. When we draw it in a 3-dimensional model to show how these bonds form, that is a structural formula. This is a structural formula. This is a molecular or molecular formula. All it does is tell me the number and type of atoms. Tells me nothing about bondings. Structural formulas tell me how they're bonded, and we represent them with lines. This line represents 1 electron on hydrogen, 1 electron on hydrogen being shared. It is a single bond. This represents 2 electrons from this oxygen is being shared here. 2 electrons from here are being shared. And so 4 in total, 1, 2, 3, 4, 2 lines, it's a double bond. H2O shows us that oxygen is doing a single bond here and a single bond here. Now hydrogen has 2 electrons, 1, 2. Hydrogen has 2 electrons, 1, 2. But oxygen is sharing a total of 2, 1 with each hydrogen. So a total of 4 being, or a total of 2 here and 2 here. So again, oxygen has 6 other electrons over here, and then it gains 1 from the hydrogens. Yeah. So it's a single bond and a single bond. And then we look at carbon dioxide. Carbon dioxide, okay, has a double bond here and a double bond here. Carbon, again, you wouldn't know this, but you would eventually, if you studied the chemistry long enough, you would just memorize that carbon has 4 electrons on the outside. So it needs 4 more. So it needs 1, 2 from oxygen, 1, 2 from oxygen. So it's 2 double bonds, okay? This is just a 3D representation. These are little toys you can buy to show what the molecule looks like in 3-dimensional space. I'm not interested in you knowing this. Okay, let's talk about chemical reactions, okay? So a chemical reaction occurs when the bonds are either formed or broken, Okay, chemical reactions are when bonds are formed or broken between atoms, ions, or molecules. So when we went back and we formed an ionic bond, yeah, that is a chemical reaction. The chemical reaction is chloride ripping an electron off of sodium, forming two ions, and then those ions forming an ionic bond. That is a chemical reaction. Sodium plus chlorine equals a sodium and chloride ion that then ionically bond together. When we talk about covalent bonds, a hydrogen atom plus a hydrogen atom forms a hydrogen or a dihydrogen molecule. That is a chemical reaction, and it forms a non-polar covalent bond. Then we can form polar or hydrogen bonds as well. These are all chemical reactions. Now, there are two aspects of a reaction. There are the reactants and the products. The reactants are the things reacting, and the product is the thing that is formed. That is it. It's not rocket science. There are two types of reactions that I really care about you knowing, but four in total. The first one is synthesis. What does it sound like? Synthesize. You build something. A plus B equals AB. We take two reactants and we create a product that is a combination. Okay? So synthesis, two or more atoms form a molecule that bond together. Sodium plus chloride equals sodium chloride. That is a synthesis reaction, in which case the reactants are two ions, a sodium and a chlorine ion, positive sodium, negative chlorine, and it forms the product of sodium chloride, a now stable ionically bonded crystal array. Decomposition is the reverse, right? We break it down. We take the reactant, which is the sodium chloride, and we break it down into the product, which is going to be the sodium and chlorine ion. So the reactants are on the left, the product is on the right. The reactant is what you're using to create the reaction. The product is what is the result of it. So don't think the product is always the bigger thing. The product can be the smaller thing. If it's on the left, it's the reactants. If it's on the right, it's the product. Now there's an exchange reaction. This is your acid-base reaction. Again, this isn't organic chemistry. I don't care if you know how to describe acid-base reactions. An exchange reaction is you exchange something. So if I have AB plus CD, it becomes AD plus CB, right? The B jumped onto the C, the D jumped onto the A. The example of this in the real world is your acid-base reaction. That's all I want you to know. Exchange reaction will look like this. AB plus CD equals A or becomes AD plus CB. The reactants are AB and CD. The products are AD and CB. And an example of this would be an acid-base reaction. Now, a reversible reaction is any reaction that can go both ways. It is a reaction in which the reactants and the products are the same and can change depending on the direction, right? So ones in which the products can change back into reactants. So if I have AB and CD becoming AD and CB, that is a reactants, A, B, and CD, becoming the products, AD and CB. But in this reversible reaction, AD and CB can just as easily fall back and become AB and CD. So that would be the reactants AD and CB becoming the products AB and CD. Okay? A reaction that goes both ways, reversible, not rocket science. Yeah? The reactants and the products change depending on which direction you're going. Now, a catalyst changes the speed of a chemical reaction. That's all I want you to know. A catalyst is something that changes the speed of a reaction. It can slow it down, it can speed it up, but if it changes that speed, it is called a catalyst. Think of a catalyst for change. The thing that causes the speed of a change is your catalyst. In the human body, we call those enzymes. Enzymes in metabolism are what create chemical reactions in the food we digest. And because they are the enzymes creating the reaction, they catalyze the reaction. Yeah, catalyst and enzyme, the same thing. A catalyst is anything that changes the speed of a reaction. In human beings, we call those substances enzymes. Acid base. Again, this is not organic chemistry. We are going to make this very simple. When you have a reaction that creates ions, those ions are called, when they're in water, electrolytes. They carry an electric charge, negative and positive, sodium and chlorine. That's why we call them electrolytes. They are creatures of electricity. Yeah? So when we have an ionic bond put into water, it dissociates. It dissociates, right? The slightly positive end of the water pulls apart the ionic bond on the negative side. The slightly negative side of water attracts the positive ion in that crystal array. Because remember, because they're not sharing electrons, they don't form molecules. They form a crystal array. They're a positive and a negatively charged ion couple that hover towards each other because they're attracted. But when we put them in water, that polar covalent bond, that slightly negative side, now attracts away the positive sodium from the sodium chloride. And the slightly positive hydrogen now pulls away the negatively charged chlorine from the sodium chloride, okay? When it does that, it creates the ions once more. We call those ions electrolytes in water. Another term for electrolyte in the human body is a salt, okay? Electrolytes and salt are the same thing. They are ions in water. When we create these ions, an electrolyte that causes hydrogen ions to release in the water are called acids. Electrolytes that release hydrogen ions into the water are called acids. Electrolytes, and this is worded so dumb, so we're going to change it. Electrolytes that cause hydroxide ions, OH negative, to form in the water are called bases. So there's a mistake here that I couldn't edit right here. The concentrations of hydrogen ions and hydroxide ions, that should be a negative, in the body create our balance of acid and base. This balance is called the pH, okay? So when you have an acid-base reaction, and again, I'm not going to give you reactions and ask you to tell me the reactants and the products. This is not organic chemistry. But when you have an acid-base reaction, you form ions in water. You drop the ionic substance in water, it dissociates back into its ions. Those ions are called electrolytes or salts. When that reaction happens, if it creates more hydrogen, H+, in the water solution, it is an acid. If it creates more OH negative in the water, it is a base. And the ratio of H+ to OH negative is how we calculate our pH. You will not need to know how, you will not need to calculate the pH. I just want you to know that it represents how many hydrogen ions or hydroxide ions are in a solution. So again, we have sodium chloride. We drop it in water. Here it is, our crystal lattice. Negative charge, positive charge, they hover next to each other. Oh, we drop it in water. Here's the water. Negatively pulled oxygen now starts attracting to the sodium in such a way that it actually forms a stronger connection and it rips it off of chlorine. Positive pull of water's hydrogen does the same thing to chlorine and it dissociates. So now in this water, we have a bunch of these guys, water molecules, which are compounds, that are hydrogen bonded to each other, creating relatively weak bonds, but together gang up on that sodium and rip it off of sodium chloride. And then over here, gang up on chlorine and rip it off of sodium chloride. Now we have in this solution here a bunch of water molecules that are compounds and a bunch of sodium ions and a bunch of chlorine ions. That is dissociation. It is an acid-base reaction, and in doing so, it creates salt in the form of sodium and chlorine ions known as electrolytes. The pH scale. Again, here's all I want you to know. It's a scale of 0 to 14. The higher the number, the more basic. The lower the number, the more acidic. A pH of 7 is neutral. Understand, because the pH is a representation of a concentration of hydrogen ions and hydroxide ions, neutral just means there's equal amount of hydrogen and hydroxide ions. There is no actual neutral state. It just means that it's equally as acidic as it is basic, okay? So anything with more hydrogen ions than hydroxide is an acid, and its pH will be between 0 and 7, but it's just less than 7, because remember, 7 is neutral. If you have more hydroxide, OH negative, than you do hydrogen, you're considered basic. Another term for it is alkaline. That is 7 to 14. Really, it's anything above 7, because again, 7 is neutral. The fact here is that between every whole number on the pH scale, there is a magnitude of 10 times more or less hydrogen ions. I don't care if you know that, right? The pH of 3 will have 10 times more hydrogen ions than a pH of 4. That's not important for you to know, okay? Just know more hydrogen, more acid. Acid exists from anything lower than 7. More hydroxide, more basic or alkaline, that's anything above 7. If it's at 7, it means there's an equal balance between hydroxide and hydrogen ions. A buffer are chemicals that will combine with excess acids or bases to help minimize the pH in the body fluids. So a buffer makes it so something really acidic becomes less acidic. Something really basic becomes less basic or less alkaline. Why would we want that in our bodily fluids? Well, it goes back to our first lecture, homeostasis. Buffers are chemicals in our body that stop the body from becoming too acidic or too alkaline. The action of a buffer is an example of a homeostatic mechanism. It achieves a homeostasis, which in blood is about 7.4, but those buffers make sure that our blood never becomes too acidic, never becomes too basic. It is therefore a homeostatic mechanism. Again, I'm not going to ask you what those chemicals are. I'm not going to ask you how they work. Just know that a buffer is a chemical that stops the acid from being too acidic and stops a base from being too alkaline. It makes an acid more basic and a base more acidic, okay? And it is a homeostatic mechanism to bring ourselves to homeostasis. Don't need to memorize any of this. It's just a good diagram. We look at neutral, distilled water, right? It is just a bunch of water. It doesn't create any more hydrogen ions than it does hydroxide ions. As we start to create more hydrogen ions, we become more acidic. Cow's milk, corn, cabbage, tomato juice, apple juice, more acidic. Gastric juice, more acidic. The more we have this in our body, the more buffers we release to bring our body back to neutral. Human blood is slightly basic at 7.4. But again, if we're drinking a lot of apple juice, we start trending towards acid. Well, we use buffers as our homeostatic mechanism to bring it back to 7.4. Further drawing from our last lecture, the negative feedback system is what tones those buffers down so we don't overshoot 7.4 and start becoming more basic. Okay? Fun fact, your gastric juices, that's your stomach acid, very acidic. There's a special lining in your stomach that protects your body against its own acid because your stomach acid, if it leaked into the rest of your body, would dissolve you. Yeah? Now, on the opposite side, more basic, more OH negative, more hydroxide concentration, we start becoming more alkaline and more basic. The human blood is slightly basic. Egg white, sodium bicarbonate, milk of magnesia, household ammonia. Again, we start consuming those things, buffers are going to come out and start making it more acidic as a homeostatic mechanism, bring us back to homeostasis, which is 7.4. The negative feedback system will slowly down-regulate those buffers so that it stops at a nice even 7.4. It doesn't continue to become acidic. Constituents of a cell. So chemicals are divided into organic and inorganic. Again, I want to keep this simple. Anything that contains both hydrogen and carbon, while it may dissolve in water, does not form ions. These are non-electrolytes, and that's because if they formed ions, they'd be electrolytes. Hydrogen and carbon, we're made of carbon. We are hydrocarbon creatures. We are organic. Organic molecules do not create ions. Okay? Example are our carbohydrates, our lipids, our proteins, our nucleic acids. They do not create electrolytes because if they did, they'd disassociate in water and just fall apart. We don't want our nucleic acids falling apart. That's our DNA. We don't want proteins falling apart. That's our muscle. We don't want lipids falling apart. That makes up our cells and our membranes. We don't want carbohydrates falling apart because that is making up our energy sources, our energy supply, and our food storage. Yeah. So organic substances do not form electrolytes. They are called non-electrolytes. Everything else is inorganic. They usually dissolve in water and they thus create ions, what we call electrolytes, or otherwise salts. So water, oxygen, carbon dioxide, salts, those all break down in the body and form ions. The most important inorganic substance is water. It makes up 98% of our composition. Now, you'll notice it says here it makes up 2/3 of our weight. Why only 2/3? Why not 98% of our weight? Well, because there's heavier things in our body that are not water. Even though water is the most abundant, it doesn't make up the same amount of weight. So it makes about 2/3 of our weight. Water is an important solvent. Again, don't get in the weeds with this. When we dissolve something in water, the fluid that it dissolves in, that's just called a solvent. Okay? Again, this isn't a chemistry class. We're not going to do solvent solute experiments. A solvent is the fluid, okay? It's the fluid in which the other substances dissolve. The thing that dissolves, it's just called a solute, yeah? So in the blood or in the water of our body, we will have ions, electrolytes, yeah? Sodium, chlorine. It will dissolve in the water, which is the solvent, creating the ions, which is the solutes, that then will be traveled around the body to use in the bones, to use in the nerves, to use in the skin, the muscle tissue, whatever. Water absorbs and transports heat, especially in our body. Remember, I've said before in class, water holds a lot of heat. We sweat water because water holds heat and we can release heat from the body, okay? So again, inorganic substances, water, oxygen, carbon dioxide, and salt. I do want you to know those. They form electrolytes. Anything that dissolves in a fluid, the fluid is the solvent. The thing that's dissolving is a solute. So if I say, in a solution of water, sodium ions and chlorine ions, what is the solvent? The answer is water. What's the solute? The answer is the ions, the sodium and the chloride, the electrolytes, the salts. Oxygen is another important inorganic compound. It breaks down in the body. All I want you to know is we breathe oxygen. Not a new fact, yeah? We breathe oxygen. Oxygen is needed to release energy from nutrients. Okay, we're not talking about it yet, but when we talk about energy production in the mitochondria, oxygen is what's used to create energy. We breathe it in. The waste created from that operation is carbon dioxide, which we breathe out. Okay? When we create energy releasing reactions using oxygen, the byproduct is carbon dioxide and we breathe it out. Again, because these things break down and reform as solutes, they are inorganic. The most common inorganic substance we're ever going to talk about is salt. That's your electrolytes, okay? Think Gatorade, Powerade, Liquid IV, Element, yeah? These are things we mix in our drinks or we drink that contains electrolytes. It's a fancy way of saying it contains salt, yeah? Oppositely charged ions, they provide the necessary ions in our bodies, like sodium, chloride, potassium, calcium, magnesium, phosphate, bicarbonate, carbonate, sulfate. These are things for our bones, our muscles, our nerves. These electrolytes play important roles in our metabolic processes. So just recognize these inorganic compounds: oxygen, carbon dioxide, salt, and water. Okay? If it's composed of carbon and hydrogen, it is organic. It is a non-electrolyte. If it's anything else that breaks down into ions, it is inorganic. It forms electrolytes. The most common inorganic substances are water, oxygen, carbon dioxide, and salt. Okay, that is the end of friggin' chemistry, okay? A lot of definitions in there, but mostly straightforward stuff. I want you to focus on the things I emphasize in this video and the things that are highlighted in the notes, okay? This is not a chemistry course. I'm not going to ask you to do chemical reaction equations. I want you to know why things are called what they are. Because when we talk about metabolism, we talk about nutrition, I'm going to be using those words and I want you to have an understanding. Now let's talk about those all-important organic substances. These are what we call our macronutrients. They are the big things we bring into our body because they make our body run. There are carbohydrates, fats, proteins, and nucleic acids. Starting out with carbohydrates. What I want you to know is a carbohydrate provides energy. Okay, it provides cellular energy for synthesizing. It also stores energy, right? Carbohydrates are what we use to store energy. We haven't talked about ATP yet, but ATP is chemical energy. When you eat a carbohydrate, say you're eating bread, you break it down into glucose. All carbohydrates are sugars, by the way. When you break it down to glucose, that glucose is digested and turned into energy. That energy is ATP. So carbohydrates break down into sugar to form energy. Don't worry about it's a hydrocarbon with oxygen, typically twice as many hydrogen as oxygen. That's not super important. We're not going to talk about the structure so much. What I want you to know is carbohydrates break down into sugar so that we can build and store energy. There are 3 types of sugars. There is a simple sugar, okay, called a monosaccharide. Saccharide is another term for carbohydrate. A simple sugar, or mono, is one sugar molecule, okay? Monosaccharide, one sugar, simple sugar, okay? It's a structure that is a ring of 5 to 6 carbon atoms. Again, I don't need you to recognize what these are, but they're sugar. Glucose, fructose, galactose, ribose, deoxyribose, these are all sugars. And because there's only one molecule of them, they're monosaccharide. Now, next we have disaccharide. Di meaning two. 2 sugars connected to each other. Again, you don't need to know these examples so much, but lactose, sucrose, maltose, these are your common disaccharides. What I want you to know is disaccharide is 2 sugars, double sugars. Polysaccharide is everything else. It is a long chain of sugars. It might only be 3, it might be 300, okay? Examples of this are things like starch, glycogen is how we store energy. So when we eat food and we don't break it all down, we store it as glycogen. Okay? Starch is a type of really complex sugar that when you break it down gives you a crap ton of energy because how many sugar molecules are on it. Potatoes are a great source of it. If you eat a potato, you get a lot of energy out of it. Again, what I want you to know, many saccharides sugar, okay? So carbohydrates, they're sugar called saccharides. They are used for building and storing energy. They come in three forms. Mono, meaning one, di, meaning two, and poly, meaning many. So what do they look like? Again, all this garbage about, oh, it's a hydrocarbon, typically twice as many hydrogen as oxygen, blah, blah, blah. This is what it looks like. In a molecular drawing, you will often see it drawn like this. This weird trapezoidal, would that be a trapezoid? Yeah, well, maybe. No, it's 1, 2, 3. Anywho, this shape here is often how a sugar molecule is expressed. It's just the fancy way of drawing it. This shape signifies a ring structure, okay? This is a mono, because there's only one ring, structure, monosaccharide. Specifically, it's letting you know this is glucose, the most common form of energy that we have, okay? This is also glucose. This is also here, glucose, right? This is just the simplified version, yeah? We can see that this shape and this shape is the same, except it's got all this junk over here, and then this is just this written out in a really long, annoying way. So again, mono, one, monosaccharide, disaccharide, polysaccharide. Look at all that crap. Now remember, each of these monosaccharides can be broken down to energy. So monosaccharides give us some energy. Disaccharides give us a little bit more energy. Polysaccharides, that gives us a lot of energy. So when we're eating our carbohydrates for the day, this gives us a lot of our nutritional energy. Polysaccharides. That's it. That's carbohydrates. That's what I want you to know. Carbohydrates are sugar that are used to build and store energy. They come in three forms: mono, di, and poly. Recognize this image. It's a ring structure. Lipids. Okay, so lipids, another term for it is fat, specifically triacylglycerides or triglycerides. Okay, again, there are a couple forms. There are triglycerides or triacylglycerides, they're sometimes called. This is the fat that we use for energy. There are phospholipids. These are a kind of fat that create barriers like our cell membranes. And there are steroids. When I say steroids, you say hormones. Steroids build hormones. They regulate the endocrine system. Okay, the hormones of our body. So triglycerides, sometimes known as triacylglycerides, the acyl just refers to a part of its structure, are your fats, otherwise also known as lipids. You'll notice carbohydrates are also sugar, are also saccharides. Lipids are also fats, are also triglycerides or triacylglycerides, yeah? Triacylglycerides are the most abundant lipid in your body. They are, oh, wait a minute. They're used to store and supply energy. Well, didn't we just say that about carbohydrates? Yes, we did. They do the exact same thing, except because of the structure of carbohydrates, all I need you to know is carbohydrates are now energy. They break down really fast by comparison. So when I need energy now, I eat carbohydrates, I get energy now. When I eat fats, that is a big, much more complex molecule that's harder to break down. So that's energy later. Okay, energy now is going to be carbohydrates in the form of mono, di, or polysaccharides. Energy later is going to be lipids in the form of triglycerides or triacylglycerides, okay? Now, why are they called triglycerides? Because they're a glycerol with 3 fatty heads. Also, the fatty heads are called acyls. triacylglycerides, a glycerol with 3 fatty heads, also sometimes just shortened to triglycerides. Okay, fatty acid with a single carbon bond is called a saturated fat. Those with double bonds are called unsaturated fats. Okay, saturated fatty acids and unsaturated fatty acids are the 2 types of triacylglycerides. So what does that look like? Well, when they have a single bond with everything, they are called saturated fats. These are very organized structures, and they often appear as solid foods. Things like stick butter. Yeah, that's a saturated fat because at room temperature, it's solid. And because of it all being a single bonded carbons here, it's a nice, even stacked structure, so it becomes very solid in its form. Again, this is glycerol. These are our 3 acyl portions, triacylglyceride or triglyceride. Now, unsaturated fats, because of that double bond, these do not stack nice on each other, so they don't become as dense. And therefore, at room temperature, they're often a liquid. I want you to know that. Saturated fats have no double bonds in them. Look at all those single bonds. They stack nice and easy on each other. This is your saturated fat. These are solid at room temperature. Unsaturated fats have that mean double bond down here. That makes this uneven. Yeah, it doesn't stack very well, so it can't maintain a density. So it's a liquid at room temperature. Those are your triglycerides. They are used for synthesis and storage of fat and energy, okay? But they're later energy. Now, the other thing I would like you to know is that carbohydrates produce much less energy than fats do. So fat is energy later, but it's a big rush of energy. Okay, remember energy is ATP. If glucose creates about 32 ATP, a triglyceride might create hundreds of ATP. That's how much energy it's creating, which is why it takes so long to create it, so it's later energy. So fats, triglycerides are the most common. They are for energy storage and synthesis later. And if it's a single carbon bonded triglyceride, it's saturated because it's solid. And if it's double bonded, it's unsaturated, uneven. It is unsaturated and therefore it's liquid. Phospholipids. They consist of a glycerol, 2 fatty heads, and then a phosphate group. Well, you don't really have to memorize that because it's in the name, right? Phospholipid. It's the same thing as the lipid, fatty tails with a glycerol, but it has a phosphate group, yeah? The phosphate head, I want you to know this, is hydrophilic. The tail is hydrophobic. Why do I want you to know that? Cell membranes, okay? So if you have water in your cell, your cytoplasm, your head of the phospholipid is hydrophilic. It's going to orient towards the water. The tail is hydrophobic. It stays away from the water. So what happens is you get 2 layers of phospholipids. The tails touch each other because they're hydrophobic. The heads touch the liquids. They're hydrophilic. And as a result, it creates a barrier that we call a membrane. So phospholipids, I want you to think cell membranes. The phosphate group is hydrophilic. The fatty acid tail is hydrophobic. It creates a barrier like in plasma membranes or cell membranes, okay? Phospholipid, phospho group. Hydrophilic head, hydrophobic tail creates cell membranes, plasma membranes. It creates structure, okay? It contains the fluid sac that is the cell. When we talk about steroids, they're complex structures. They're carbon rings. They will look similar to carbohydrates when you draw them. But what I want you to know is steroids are 2 things: hormones and cholesterol. They are part of the endocrine system. When I say steroids, you say hormone. Okay? The most important form of one of the most important forms of steroids is cholesterol. Okay, they are used to synthesize several hormones, including sexual hormones. Okay, and they are formed in the adrenal gland. Sorry, they form the hormones in the adrenal glands. Okay, so phospholipids, yes? Let's take a look at it. We have the glycerol here. Then we have the 3 fatty heads. This is a triglyceride. Now, when you add this phosphate group here, this is a phospholipid. This is what it looks like. So this is water hydrophilic. It likes the water. This does not. This creates part of the barrier. If you have 2 of these back to back, you have a head up here and a tail down there, no water can get in here. That is your barrier. That is your cell membrane, your plasma membrane. There's your structure. This is what a steroid looks like. So similar to carbohydrate, right? Except they directly touch each other generally when they're drawn. Again, I don't need you guys to really know these structures because they're just illustrations. But know that when I say steroid, you say hormone, and one of the most important one is cholesterol. Oh my God, look at this. Learn this. This is it. All the other slides right here, boom. Triglyceride, most common lipid in the body, stores fat tissue for energy. I want you to know later energy, okay? Also, yeah, fat provides thermal insulation of your skin. One of the layers of your skin is made up of entirely fat. It's called the subcutaneous fat, yeah? 3 fatty acid molecules or achial molecules bound to glycerol. Now, if you take a triglyceride and you add a phosphate group, it's a phospholipid used in the structural components of cells because one side's hydrophilic, one side's hydrophobic. It forms a double layer that creates a watertight barrier, creating your membrane, yeah? It's abundant in the liver, parts of the nervous system. Wherever fat is used for structure, it is a phospholipid. Steroids, 4 connected rings of carbon atoms. Cool. Widely available in the body for a variety of functions because it is your hormones. The most common type is cholesterol, but it also forms the hormones in the adrenal cortex, which is your adrenal glands, and the hormones in the ovaries and the testes. Again, hormones, 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 hormones. All right. Next group, proteins. Proteins, I want you to understand, are your building blocks for muscle and structure. If phospholipids are your structural shape, the proteins build the thing, right? So phospholipid creates your cell membrane, the protein creates the parts in the cell, okay? Again, I don't care that you know it's a carbon, oxygen, hydrogen. I do want you to know that there's nitrogen in there, but we'll get to why in a second. A variety of functions in the body. They are your structural materials. They are your building blocks for muscle. They help with energy and hormones, blah, blah, blah. I want you to know they're the building blocks of muscle and bone, okay? They play a role in immunity, muscle, bone. That's what I want you to know about proteins. Proteins consist of building blocks, all of these things do, called amino acid. For carbohydrates, it's your saccharides, mono, di, poly. For fats, it's your triglycerides, phospholipids, steroids, right? For proteins, your building block of a protein is the amino acid. Now, an amino acid, and we're going to go through this slowly a bit, contains a carboxyl group, an amino group, and the R group. We'll keep it simple. Every amino acid has the same carboxyl group and amino group. The R group tells us what kind of amino acid it is. Now, there's roughly 20 different amino acids that humans digest. There are more than 20 amino acids, but for humans, 20 is what's important. There is one amino acid that only plants can break down that we can't. When we take our amino acids and we build them into long chains, they are called a polypeptide chain. Okay, like sugar, right? Carbohydrates are also called sugars, are also called saccharides. Proteins are also called amino acids, are also called peptide chains. Okay, Polysaccharide is a long chain of sugar, is a big carbohydrate. A polypeptide chain is a big protein with a long chain of amino acids. Amino acids bind together to form these big protein chains. They're enormous. They're hundreds, if not thousands, of amino acids to form a protein. Okay, so this is a protein. This is a protein. This is a protein. You will notice this junk, this junk, this junk, identical, the exact same. This is your carboxyl group. Your C double bond O single bond OH is called a carboxylic acid. You don't need to know that. This is your carboxyl group. This with a nitrogen is your amino group. Your NH2 is your amino group. Okay? That I do want you to know. Carboxyl group, amino group. The R group is different depending on the protein, depending on the amino acid. This R group is cysteine. Okay? This R group is phenylalanine. You don't need to memorize all these. Just know the R group tells us what amino acid it is. It's what makes the amino acid unique, because everything else is the same. Every amino acid, the exact same amino group, the exact same carboxyl group. The R group determines what amino acid it is. Now, like carbohydrates have mono, di, and polysaccharides, okay? Proteins have different level of structure, okay? So when we make proteins, we could have a protein that is in a primary, secondary, tertiary, or quaternary structure. Primary structure, all I want you to know, it's just the sequence of amino acids. This is what it looks like up here. It's just a long chain of amino acids. Nothing special about it. That is a primary structure protein. Secondary structure, here's what I want you to know. Pleated sheet, twisted coil. Okay? It's caused by the hydrogen bonding. Yeah, remember, hydrogen bonding is really weak bonds between the hydrogens in molecules, okay? So see all these hydrogens out here, all these hydrogens out here, all these hydrogens, they start reacting with each other in such a way that it takes this long chain and either turns it into a big coil or creates this, what we call a pleated sheet appearance. If I say pleated sheet or coil structure due to hydrogen bonding, that is your secondary structure of a protein. Your tertiary structure is a unique fold of the protein due not to the hydrogen bonding, but now the bonding between the amino acids. This bonding relationship to this is now creating more complex folds. So now you got all this crazy stuff happening. It started like this. And then some of the hydrogen bonding caused some of these, oh, look at that, a coil. Oh, that zigzag, maybe that's a pleated sheet. And now it starts really wrapping and getting all congealed. That's your three-dimensional folding. Three-dimensional folding, three tertiary structure. The last one's quaternary. Here's all you need to know. Quaternary is tertiary, except instead of one chain of amino acids getting folded into pleated sheets, coils, and then folded into a tertiary structure, we have multiple tertiary structures all folded together. That's quaternary. When there are two or more polypeptide chains combined. So again, tertiary, it forms this big glob like this. Well, now when you add multiple globs, that's your quaternary structure. So proteins, they are your building blocks for bones, for muscle. They play a role in the immune system. They are made of long blocks of amino acids. The amino acids contain the carboxyl group, the amino group. How do we know what amino acid it is? The R group. The R group is the only thing that ever changes, okay? a long chain of amino acids is called a polypeptide chain. Why is it a peptide? Because the bond that forms the amino acid is called a peptide bond. So many amino acids, many peptide bonds, polypeptide chains. When we're forming our proteins, because right now we just have amino acids, long chains of amino acids are now a protein. Okay, the proteins have complex shapes. They can be primary structures, which is just a long sequence. It could be a secondary structure where that long sequence has now formed into folded pleated sheets or coil structures. It could be tertiary, where it uniquely folds into a three-dimensional shape due to the attraction of the amino acids. Three-dimensional shape, that's tertiary, that's three. Or it could be quaternary. It could be multiple long chains all folded together. Each of these are different types of proteins with different structures. They're all proteins, but they all have different structures. When we're talking about proteins and doing the action that a protein does, we talk about conformation and denaturation. Conformation, okay, this is the function of a protein. What I want you to know, conformation, confirm. When you have a conformation, you have a determined function. You confirm the function of a protein, okay? That's all I want you to know. The conformation of the protein is its determined function, okay? Denaturation, D meaning against, nature, shun, state of, denatured state. It is the irreversible destruction of a protein shape such that it does not function anymore. It breaks the bonds, okay? Excessive changes in temperature, radiation, chemical exposure, pH, all of these things can denature proteins. Conformation determines its function. It is the active state of the protein doing protein stuff. Denaturation is when you've destroyed the protein, okay? If I put an egg in boiling hot water, I boil the albumin in the egg and I break that complex protein called albumin down into its amino acids. That's why when you eat an egg, it is a great source of protein because it's already boiled. If it's a hard-boiled egg, you've already denatured the protein, which means your body's ingesting straight up amino acids that your body can then take into the blood, travel to the muscles, to the bone, to the immune parts of the body, and start plugging it in for building blocks, okay? Most of digestion is about denaturing protein so that we can use it in the body. Most of our cells' function of building things with proteins is conformation, because that's the function of the protein, building stuff. When we eat food, we denature proteins to break it up into our building blocks. When we use those building blocks to build us, the muscle, the bone, the immunity stuff, we confirm the protein. We use conformation to do it. We build it. All right, last subject, nucleic acid. Nucleic acids are going to be the things we talk about with building protein and DNA. So nucleic acids, they form the genes that tell our body how to build protein. They're a large organic molecule. Oh, they have carbon, hydrogen, blah, 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 blah. Don't care. They have nucleotides. That's what I want you to know. The component part of a nucleic acid is a nucleotide. A nucleotide contains a sugar, a phosphate group, and a nitrogenous base. So kind of like an amino acid, right? There's a carboxyl group, an amino group, and then an R group. A nucleic acid has nucleotides that are formed of sugar, phosphate, and nitrogenous base. A nucleic acid molecule are just long chains of nucleotides. Again, nucleic acid, nucleotides, just know that they go together. Nucleic acids are made up of long chains of nucleotides. Nucleotides have a sugar, a phosphate, and a nitrogenous base. There it is. There's a nucleotide, a sugar, phosphate, nitrogen base, nitrogenous base. What nucleotide are we talking about? That depends on the sugar. There are two types of nucleotides that are related to sugar, right? Or that are defined by sugar, I should say. RNA and DNA. The special one here, adenosine triphosphate, ATP, that's chemical energy. We'll get into that in a second. But RNA, what I want you to know, single-stranded. It's not like DNA where it's a double helix, right? RNA is single-stranded. It stands for ribonucleic acid. Oh my God, what type of nucleic acid are we talking about? A ribonucleic acid. How do we know it's a ribonucleic acid? Because the sugar is going to be specific to it. What is that sugar going to be? Ribose. That simple. Ribose is the sugar in the nucleotide. And if you see ribose, it is a ribose-containing nucleic acid, a ribonucleic acid, an RNA. It is single-stranded, and what does it do? It creates proteins. RNA is the genetic coding for protein. RNA is used to create protein in the body, okay? So when we ingest our food, we break down food into amino acids. Amino acids are the component parts of proteins. Nucleotides called RNA come along and they take those amino acids and they turn them into protein. They are the codes for how to assemble those amino acids into protein. They are single-stranded. Adenosine triphosphate is a specific type of RNA that has 3 phosphate groups. So again, it'll have a nitrogenous base, everything does in nucleic acids. It'll have ribose, but instead of 1 phosphate, it'll have 1, 2, 3. It is energy. That's all I want you to know. Our ATP, energy. It's chemical energy. It's a type of RNA. It's chemical energy. The mitochondria is the powerhouse of the friggin' cell. It creates ATP. ATP is nucleic acid. What kind of nucleic acid? It is RNA. You just got to memorize that part. Deoxyribonucleic acid, DNA. Well, it's the same game, everybody. What is it? It's a nucleic acid. It's in the name, Na. Deoxyribonucleic acid. I wonder what unique sugar it is. Well, it's deoxyribose. Yeah, the unique sugar is deoxyribose. A deoxyribose nucleic acid, deoxyribonucleic acid, DNA. DNA, we should all know this. It's double-stranded, twists into a spiral. We call it double helix. Fun fact, the bond that holds the double helix together, it's hydrogen bonds. They're just weak hydrogen bonds. So this stores the molecular genetic code for genes. Genes are used to tell a cell how to synthesize proteins. So it starts with the DNA. The DNA is used to create the RNA. The RNA is used to create proteins. That's how it works. Okay, that's what I want you to know. What I'm about to say next is a little bit of context. So in the DNA is in the nucleus. It's a big bulky structure. It can't escape the nucleus. So we create RNA, the single-stranded structure, which is much smaller. It can leave the nucleus and it can go to the parts of the cell that are then going to build the proteins. So it starts in the nucleus with DNA. We create from that RNA, single-stranded, that travels out of the nucleus, that then, with ribosomes, build proteins. That's the story. Okay? Now, if the RNA goes into the mitochondria, then it becomes energy. Okay? ATP. Blah, blah, blah. Okay? Deoxyribonucleic acid. What kind of sugar does it contain? Deoxyribose. I could ask that question. What does it look like? A double-stranded double helix. What is it used for? It stores genetic codes for genes that are used to synthesize proteins. RNA, what kind of sugar does it have? Ribose. ribonucleic acid, okay? What is its function? It functions in protein synthesis. How many strands is it? Single. Adenosine triphosphate. What is it used for? Chemical energy. Those are the questions, yeah? What's it look like? RNA. It's a single strand. These are a bunch of nucleotides creating a long chain of nucleotides. This is your RNA, okay? Now, the nitrogenous bases, okay? The nitrogenous bases, so when we build protein, the nitrogenous base is the code, right? This is the sugar, ribose. This is the phosphate group. The nitrogenous base is the code. When we have RNA, the letters we have is A, U, C, and G. We have DNA. We have phosphate. We have sugar. Deoxyribose is the sugar. We have the nitrogenous bases. You will notice similarities, A's, C's, and G's. This is the hydrogen bonding here between the double helix, and this is all twisted, obviously. So the nitrogenous bases, when we code our DNA, there are 4 different bases: A, T, C, and G, okay? Guanine, cytosine, taline, adenosine, yeah, okay? They work in pairs with each other. So if this side of the DNA has an A, the other side is a T. If this side is a T, the other side is an A. A and T are a pair together. Apples are in trees. When I say A, you say T. When I say T, you say A. If a DNA sequence is ATA on one side, the other side is TAT. The same goes for C and G. Your car gets parked in the garage. If I say C, you say G. If I say G, you say C. So here we have 2 strands of our DNA. We have a long nucleotide chain of DNA. We have phosphate group. Deoxyribose is our sugar. We have a nitrogenous base that is going to code our proteins. These are our genes. This is our genetic information. There's only 4. The long order in our DNA is what our gene codes are. Okay? So if I was to give you this strand of DNA, I need you to be able to produce this strand. So if I say the DNA sequence is A, T, C, G, A, T, you need to tell me the other strand is T, A, G, C, T, and A. They are pairs. Apples are in trees, cars are in your garage. With RNA, it is a single strand, but because this is what we use to build the protein, the pair that we bond to it breaks off as the protein, okay? The U stands for uracil. The U is the same as a T. It is the same game. If I say the RNA sequence is AUCGAU, the protein sequence is now UAGCU and A. In RNA, apples are under the tree. Cars are still in the garage, okay? So RNA, single strand, and if I say, hey, the RNA is AA or is AUCGAU, or I could make up any order, you need to be able to tell me the protein sequence being the opposite, okay? DNA, if I give you one strand of DNA, you should be able to give me the other. All right? Adenosine triphosphase, okay? This is the unique nucleic acid. I don't really care that you know this. It's an RNA variant. It's ribose sugar. And instead of a nitrogenous base, because it's not used to program genes or proteins, it's just adenine. Yeah. So adenosine is the word for the phosphates, triphosphate. Adenosine is the compound between adenine and ribose, so adenosine triphosphate. Again, I'm not going to ask you to draw any of this. Just know ATP has 3 phosphates. It is a version of RNA, and it's used for energy. Okay, so my question might be, which nucleic acid that is composed of adenosine and 3 phosphates? And your answer should be adenosine triphosphate. Not too rocket sciencey. Which nucleotide is composed of a phosphate, a nitrogenous base, and a deoxyribose sugar? Your answer better be DNA. If I say which nucleic acid is composed of a phosphate, a nitrogenous base, and a ribose sugar, your answer better be RNA. And if I say the RNA sequence is AUC, you better be able to produce to me the sequence opposite that is UAG. And if I say the sequence of DNA is CGT, you better be able to say the component part on the other side of the helix is GCA, right? That's what I want you to know about these things. Oh my God, look at this. Another really convenient breakdown. Now, it doesn't quite have all the information I want you to know, but this is a really good starting point. Again, I don't care about the elements. I don't. That does not matter. This is useless. Carbohydrates, they provide energy. They are energy provisions, yes? They produce energy now. They come in the forms of monosaccharide, disaccharide, poly. 1 sugar, 2 sugar, many sugars. Lipids, there are 3 types. We also call them fats. Triglyceride or triacylglyceride, which is for energy, big energy, later. Then we have phospholipids with a hydrophilic head and a hydrophobic tail. They create the cell membranes and help provide structure. Then we have steroids. One of the most important ones is cholesterol, but I want you to know hormones. Proteins are coming in the form of polypeptide chains or amino acid chains, yeah? They have a carboxyl group, an amino group, and an R group. The R group tells us which amino acid it is. They provide structure in our body they provide the building blocks for structure. Things like bones, things like muscle, playing a role in immunity, okay? They come in primary structure form, which is a long chain, secondary structure form, which is a pleated sheet or a twisted coil, tertiary structure shape, which is a 3-dimensional fold, or quaternary structure shape, which is multiple 3-dimensional tertiary structures all connected together. Okay? Examples, although you don't need to know this, things like hemoglobin, albumins, yeah, those are examples of proteins. When proteins are building things, they're conforming. That's conformation. When proteins are destroyed, it's denaturation or denaturing. Nucleic acids, there are 3 types I want you to know. RNA, which has a special variant called ATP, and DNA. They're made up of nucleotides, specifically a polynucleotide chain. They are composed of a phosphate group, a nitrogenous base, which is going to be ATCG, and in the case of RNA, U instead of T, and then a sugar. The sugar tells us which type. If it's RNA, it's ribose, ribonucleic acid. If it's DNA, it's deoxyribose, deoxyribonucleic acid. If it is ATP, it's adenosine, okay, which stands for adenine and ribose, sorry. Then the unique thing there is it has 3 phosphate groups. It is for energy production and storage, ATP. RNA is used to produce proteins. DNA is used to produce RNA. Yeah? Because DNA is big and bulky, can't fit outside of the nucleus, but RNA can. So that's how it gets to the cell to produce our synthesis, or to synthesize our proteins that are used for cellular activity. Okay? That's it. Awesome. I'm going to upload this as well as the new notes and try and get this viewed so you can get the assignments done by class on Thursday. Today is Tuesday, so tomorrow night, by tomorrow night, I will also have our next PowerPoint presentation up that we will be going through in class. Okay? All right. Thanks, guys.